You unbox a pristine, high-tech machine, send your file, and watch as it spits out a faded, bleeding mess. The immediate reflex is to blame the hardware. You run printhead cleaning cycles, check the ink supply lines, and dig into the mechanical settings. But if the mechanical diagnostics come back green, the internal hardware is executing its code. You've hit a dead end because the problem isn't occurring inside the printer's logic. The printer sits exposed to the room, a reactive entity in an open system rather than a closed mathematical box. When the machine is functioning as designed, the search for the saboteur moves away from the internal components and toward the invisible space surrounding the printer. The first external variable sits entirely outside the machine's casing. It is the microscopic topography of the paper you feed into it. Paper is a chemically active landing zone, governed by something called surface energy. This property dictates whether a material acts as a tight, water-repellent shield or an absorbent sponge. This diagram shows a material with high surface energy. The ink droplet holds its tight, domed shape on top, delivering maximum color density. Lower the surface energy, and the droplet collapses. It bleeds outward and sinks deep into the fibers, washing out the color. A perfectly calibrated printhead cannot save an image if the chemistry at the point of impact forces the ink to fail. Now, consider the single tiny millimeter of completely empty airspace separating the printhead nozzles from the paper below. That tiny gap is actually packed with airborne electrostatic charge generated by the ambient temperature and humidity of your room. This vector grid models the intended physics. Microscopic ink droplets fire straight down, calculated to hit exact coordinates. But ambient static charge acts like a magnet. It hijacks the droplets mid-flight, pulling them horizontally. They miss their targets completely, leaving empty streaks. Perfect mechanical aim becomes irrelevant if an invisible electromagnetic field intercepts the payload in midair. Moving away from the airspace, we hit the microscopic borders of the machine's maintenance zones, specifically the capping station, which keeps the printhead sealed and moist. Fluid dynamics fail when a single microscopic air bubble enters the line. This schematic shows the capping station failing. A single flake of dried ink wedges into the gasket. It breaks the airtight lock, exposing the entire fluid system to the open air. These roadblocks compound quickly. A millimeter of contamination at the seal dries out the lines and ruins meters of final output. The internal engine fails because of negligence at the external borders. Chemical surface energy, electromagnetic static, and micro debris represent the three primary external factors that dictate print quality. The machine functions as a sensitive environmental sensor, reacting to the specific humidity, charge, and particulates of the room. This split-screen blueprint illustrates the requirement for long-term print quality. You have to zoom out from the hardware on the left and actively manage the environmental metrics on the right. Success requires matching material chemistry to your ink, neutralizing the static fields in the air, and maintaining microscopic hygiene around the maintenance zones. Now that we've diagnosed the environment as the true saboteur, we can begin to control it. In the next video, we will walk through the exact steps to engineer your printing space.